Welcome to Bisection, the movie. So, we want to determine the root of the equation. Just so we know what we're looking for, let's point out the root. It's the value of x such that the function is 0. So we find the 0 on the axis, go over to the graph, and trace down to see what the value of the function is. In this case, it's 1. So we remember that, but of course, we don't actually know this, so let's erase it. But that's what we're going to be homing in on. Okay, so visual inspection is great for locating roughly where the roots are. But the precision is pretty limited. Whatever the resolution of the graph is the best we can hope to do by visual inspection. So next, we need to locate the bounds. We're assuming that we have one root in our bounds, and it's a single root. We won't deal with the other cases right now. Drawing a lower and an upper bound, we see that the function is indeed positive for the upper bound and negative for the lower bound. So, got our bounds, draw the function. We can see that the sign changes when we go from one bound to the other. Now, if the graph was tilted the other direction, if it sloped down instead of sloping up, then the upper bound would have negative function value, and the lower bound would have a positive function value. But in any case, they would still have a switched sign. Okay. Now, what's the approximate error at this point? Well, it's just the width of the interval. It's the difference between the last two guesses, which is just that interval length. We know that the true error is less than that because the true answer is somewhere in between those bounds. So therefore, the distance between either of those guesses and the true x, that is the root of the function, is less than the distance between those 2 points. Okay, so let's evaluate. Yes, so the next step is to take the midpoint between the lower and the upper points and then evaluate the function at that point. We now have to decide which of these two sets of points bound the root. If both functions are the same sign, they must be on the same side of the root. So we're looking for the pair for which the function changes sign. Now, notice we're not using any other information about the function values here, only whether or not they switch sign between them. So looking at it, we can see that our new guess and the upper bounds are both on the same side of the root. They both have positive function values, whereas fxl, the lower bound, that's negative, and fxr, the function evaluated at our guess for the root, is positive. So those have those different signs, and those must be our new bounds. So we can get rid of the upper bounds, and now you can see our guess has now turned from our xr, our guess for the root, to an upper bounds. The approximate error has been cut in half because now we know that our function value is somewhere between these two bounds. So one step, we've cut the error in half. So we can do the same procedure. We've come full circle. We've come to the same point we were before, and then we just repeat the same procedure. So you can see this is the what we're going to be putting inside the loop when we code this up. So we take the midpoint, evaluate that, evaluate the function at that point, and check the signs. And now we can see that the upper bounds and our new guess are on either side of the root. And the guess and the lower bounds are actually on the same side of the root. So we can get rid of the lower bounds, and our xr, our x guessed for the root, is now a lower bounds. And of course, the approximate error has been cut in half again. We keep this up, the approximate error decreases by a factor of 2 every single step. We can keep on doing that until we've converged the answer. As long as we've bounded the root, as long as we've bounded a single root, it's guaranteed to converge.